right, so let me explain basically what this idea is, or this situation is. Let's imagine an object undergoing gravitational, like a gravitational pull that causes it to accelerate in only one direction. Let's say downward. It doesn't really matter what direction, but let's just assume downward. Okay. Now, because of this, usually we reach a terminal velocity after some time because of air resistance, when whatsoever. But let's imagine there's no air resistance. Imagine we're accelerating through space, and there's no other object in any like radius that can possibly pull it in a different direction. There's only one massive object pulling this other object towards itself through such a large distance in which there's no other thing filling that gap, where it's being pulled and being accelerated at such a large point at which it might or might not reach the speed of light. And that was the question posed. Now, Kushagra, what he did was he derived this, he tried to solve this fictional case and ended up deriving Schwarzschild's solution, which is the ratio between the mass and radius of a black hole. And so we're wondering why exactly or how exactly he managed to derive that, because it seems quite random if you're just trying to solve a basic fictional question, and all of a sudden what ends up happening is that you somehow derive a solution related to black holes, which is not even mentioned inside the question. So we did some digging, and what we found out was the acceleration that we were using here it has to be practically infinite, because we're not trying to limit ourselves, because if we do limit ourselves, there's no way it's going to reach the speed of light. And the only time gravitational acceleration is infinite is is past the event horizon of a black hole. And what else does Kushagra, and this exact distance between the event horizon and black hole in which the object is placed is r, meaning the radius of the black hole. So what Kushagra might have derived is literally that. Now, I think Kushagra can continue on that point.
So these are the symbols that have been used throughout. So I recommend you go through these first, and then we can start the derivation. Right, so this is the Newton's formula, the Newton's gravitational formula. And this is the Newton's second law, force equals mass into acceleration. But we have made sure, like we have assumed that only only one of the bodies is accelerating, even though this is not realistically possible. But we have made the assumption that one body is completely stationary, and it is the one exerting the gravitational pull. So this is how we have derived the acceleration, the initial acceleration, right? But now the initial potential energy equals the final kinetic energy following the conservation of energy. So initial potential energy would be, as you might know, mgh, right? So over there, m is the mass, g, which means acceleration, which is a, and h is basically the distance, which is r, right? It equals the final kinetic energy, which is mv square by 2. That's how I have written it. But over here, we talk about v, right? But we have made another assumption that the final velocity should equal the speed of light. So mar equals mc square by 2. Now dividing both sides by m, we get ar equals c square by 2. Another way of deriving this would be the distance equals average velocity into time, while the acceleration equals the change in velocity by time. So now I've substituted the value over here. In this formula, I have put the acceleration value as this much, right? And this is the equation we get. So one side we have r square and one side we have r. We can cancel those off. So we get gm by r equals c square by 2. Now dividing both sides by g, we get m by r equals c square by 2g. So this is the mass, and the r is the distance, right? But when we get m by r equals c square by 2g, the mass is for the black hole, and r represents the radius of the like from the center to the event horizon. So kind of like the radius of the event horizon.
Yep.
So that is what r is. Now Vamsi is gonna tell you why we arrived at Schwarzschild's radius.
Right. So I think I've explained it quite well last time, but I'll do it again. So how it works is, if you hover at a distance r from the center of the black hole, what happens is basically the it's quite of a mind-boggling thing. More of a, it's not really that logical, but it's the most logical at the same time. What we're doing is that the gravitational force that's exerted has to be able to cancel, or like not force, gravitational acceleration, the pull basically, should be able to cancel out any other speed that's going past it, or velocity that's going past it. It needs to be able to completely deny any escape from any energy, anything like light, object, anything. So that must be so I guess powerful that it must be able to negate all those things, and hence why we're assuming that we reached the r being the radius of the black hole to the event horizon because of this property, which is that the gravitational acceleration goes to infinity when you go past the event horizon of a black hole. And well, this is also the event horizon of a black hole is literally called Schwarzschild's radius as well. So if you think about it, it's just a bunch of connecting things that Schwarzschild has just placed for us to solve. And as soon as even when we solved it, there is no gratitude in anything because it's already been solved like what, some 100 years ago by some random scientist. So that was kind of disappointing, but I mean it's interesting just to think about it itself. You know, the weirdest thing is that literally only some of us here.
Okay, yes, but anyways, so this is for like, this is the force and the acceleration. Using these, we have derived this, and but this only explains what happens till the object approaches the event horizon. But after the object, like the object is still being pulled towards the hole, right, towards the center. So Vamsi said that the acceleration at that point should be infinite since nothing can escape it, right? That makes sense. But I believe that it should not be infinite. It should be huge, right? Because the objects that are approaching,
yeah,
huh?
Nothing can be infinite at that point.
Exactly. So the objects that are approaching the black hole and have crossed the event horizon, they can't experience infinite acceleration. But the maximum speed they can have is the speed of light. That's correct, right? That's what Einstein proved. So if the maximum speed they can have is the speed of light, and with that speed they go into the black hole, that means that the acceleration is higher than what it needs to be for objects to escape. But I believe that there has to be an upper end for the acceleration that depends on, say, the radius of the hole. Radius as in the event horizon radius. Because from there it starts experiencing the pull, the major pull. So this topic is open for debate. When an object approaches a black hole and crosses the event horizon, does it experience finite or infinite acceleration?
I'd like to point out something over here. Okay. I'd like to read something out, in fact. So in particle physics, this is the that I'm reading right now. In particle physics, as of now. We describe particle interactions as contact. In that sense, they transfer momentum and thus velocity instantaneously. It is obvious that in such a process, acceleration has an infinite peak in the moment of interaction. Now, in the case of a black hole, there is not only one moment of interaction, it's an infinite moment of interaction because you don't really it's not like you escape the black hole, but it's not like you're inside the black hole. It's very hard to tell what's going on in there. So in that case, I'd assume that this moment of interaction would not have a limit itself.
Okay, but how would you define a moment of interaction?
Well, like here's the thing. When you two particles at each other, they're going to interact in the sense that they're going to transfer momentum, right? Right?
Yes.
Yeah.
Okay, so in that sense, they're only going to do that for, I think it's finite, but I have to do my research. Okay, Shubham, good for you, man. But here's the thing: if that interaction is like the tiniest interaction, it won't last forever. That momentum will be transferred, and they're on their own days. They're not going to bump into each other, then hold on to each other forever. They're just going to transfer momentum, then immediately deviate from each other. They're not going to hold on. But in the case of a black hole, that holding on is basically infinite. Well, look, I agree that it should be finite, right? But when we derive the solution, the only way it could be derived is for it to be infinite. So I'm just putting in my logical reasoning over here, not what.
So you're just trying to assume it's infinite.
I'm not trying to assume. I'm saying
Just
that
trying to prove.
I'm not trying to prove either. I'm saying we've literally proved something because it's infinite. So if we didn't prove that if it's not infinite, then what we did over there, it makes no sense, because why would we be able to derive Schwarzschild's solution otherwise?
Okay.
Okay, well, when we talk about deriving the Schwarzschild solution, we never talked about what happens when it crosses the event horizon, right? I mean, the object is at the event horizon, and we have equated that potential energy to the final kinetic energy, assuming there was no initial energy, like initial velocity or kinetic energy for that matter. So I don't think this logic works out.
No, I think that I mean that the
No,
logic
but-
doesn't work out, but when you think about the event horizon and how
No, look,
how-
listen to me.
what
For
you say something?
infinity acceleration, you need infinity gravity, hence you need infinity mass, and black hole has a finite mass, you know.
Okay, he got you on
Yeah.
the point. That's a valid point.
Wait, what do you say?
So like it cannot have infinity acceleration because there's no infinity gravity, because black hole does have a finite mass.
I'm sorry, can you just repeat that?
Okay, look. In order to have infinite acceleration, you need infinite gravity. In order to have infinite gravity, you need infinite mass. But
And
black hole does
No,
have
we're
a
not
mass.
saying we're not saying infinite gravity. We're saying the infinite gravitational acceleration. Look, if
Yeah,
it was
but then
infinite
in
gravity,
order
then-
for the acceleration, you do need gravity, you know.
You need gravity. for
yeah, but that
Mm.
gravity doesn't have to be infinite in that case.
It
You
has
don't
to
even
be.
need gravity. You don't even need that much gravity for it to even be pulled. We're not saying the pull is infinite. We're saying that after reaching the event horizon, the object will accelerate infinitely.
Yeah, but in order to do that, the gravity should be strong enough to do that, you know.
It is, you don't have to be strong enough, bro. If there's like a core of a star, it would totally work
Then
out.
you're just telling if the Earth was big enough and something passed
Listen,
through,
man, you get
it would reach an
get
infinite
spaghettified.
acceleration.
You know how inside a black hole you're supposedly get spaghettified, like stretched, like
Yeah.
Technically, but it's not really proven, you know.
Yeah, exactly. It's not proven, but it should technically happen, which is exactly what's happening here. By technicality, it should be possible.
Yeah, because the gravitation pull is so much that will like spaghettification. That's what
Yeah,
it's called.
so that's because the gravitational pull
Or we
exerts.
just tear apart.
Yeah, well, no, you tear apart after it's spaghettifying. It is what supposedly happens, but we're not sure. Look, according to particle physics, at least, it should be possible, and according to quantum physics, it should be possible, and it shouldn't be possible because quantum physics, everybody hates that. God,
But then, according
Yeah, it's
to
just
what
based
you're
on
telling, it's like
probability.
if Earth had a
Quantum-
gravitational pull, suppose you have a radius, right? The gravitational pull affects an object. If it's big enough, it's like it might reach infinite acceleration. That's what you're telling.
No, I'm not saying that's not what I said. Listen, let me try to explain to you
It's like
in more simple words.
you're
Listen
you're
here.
being like, even if
Can I
the
share my
gravity is
screen?
weak, if it's big enough, it can cause an object to reach an infinite acceleration.
Hold on. Let me explain. Can I share my screen?
Yeah.
And is that a thing?
So
Obviously.
the Kushagra, so a black hole is just the compressed energy of its star.
Bam. Can you see this? Is this visible?
Yeah, yeah.
All right, sick. So let's say we got a little black hole dude over here, right? Sick. It's not black, but it's definitely a hole.
Right.
It's black, okay? Bam.
Black
then
holes
we
are
got
not
some.
necessarily black, but sure.
Yeah, no, it's because no light escapes it, which is exactly my point. When you go over here, bam, light beam. What happens? You think it just goes casually escaping it, Shibam? Is that what you think?
Obviously not.
Yeah,
Right?
just
It gets
like that.
now tell me, is that because it has a high gravitational pull? Or do you
Yes.
think is it because it has infinite gravity?
Yes.
No.
It doesn't, bro. You just said that it doesn't have
I didn't tell
infinite
it doesn't
gravity.
exactly. It doesn't have infinite gravity. It doesn't have infinite gravity, but it has a strong gravity.
Yeah,
Strong
well,
gravity, yeah.
by
Strong enough to
technicality,
pull the light.
yeah, nothing should be able. Exactly, nothing should be able to.
Bro, look, the
light shouldn't be able to
gravity
do
is
it, right?
literally strong enough to change time there, okay? So
Yeah, so you think this? So when light goes in, it goes into the black hole, right? But let's say a little Sambhav casually walking around. He's like, "Hey, my name is Sambhav. I'm gonna walk around, right?" Do you think he'll get pulled at the exact same stream of acceleration that this light beam got accelerated at, or do you think it'd be different? Because if that was true,
Different.
we wouldn't even be able to know if Sambhav was even here or not. He'd immediately be sucked into there.
No, I
not
have
in the
one. Because of
beginning, but
Sambhav,
maybe in the end.
No.
If Sambhav's speed is like 5, then this thing's velocity is 5, then this thing should be at least like -5. It should be able to negate everything.
But here's the
This
thing,
should
we
be-
still don't know if it
this
has
is
a
the-
limit, right?
Yeah, but look, if this is C, then the gravitational pull should be -C. It should be able to negate literally everything.
So 0.
Okay, look,
Yeah.
let me give you an example, right? I know Earth physics doesn't work outside of it, but then everything has like a maximum point it can travel, or like a maximum
The
speed
limit.
it can go in, right?
Let
There's
me
a
ask you
limit. There's always a limit.
Let me
Right?
ask you something.
So
Are you
eventually they
familiar
both
with
would go in the
Are you
same speed.
familiar with the video game Among Us?
Yes.
Let me ask you something.
I'll tell you what you're saying, right? If you're saying that the
Yeah.
acceleration must be infinite, then you know the Newton's law, right? The Newton's gravitational law. You're
Yeah.
proposing that the distance between the center of masses be 0. Is that what you're saying?
No, I'm saying that past the event horizon. And I mean, not exactly the distance between the two objects, but yeah, sure.
See, but it can't be like, it's only possible when the distance is 0. I'll just share my screen. So, you know how there are like limits for distance. I mean, the distance is continuously decreasing, right? It's becoming 0,
Yeah.
right? And what's the closest distance can be to 0? Like, I mean, Planck's
Planck,
constant,
Planck's constant.
which is represented by H over here. So, I think this would be the acceleration.
Like, dude, listen, I think I found out something crazy, right?
Let me
Okay.
ask you. Let me explain something to you then, right, man?
No, wait, let
Think
me
about,
tell
like,
something.
Someone
Dude, relax.
Okay, listen to me. Okay, I have the most crazy revelation you'll never understand in your life. All right. If the event horizon represents the point of return, no return, even for light, then are we saying that the surface gravity of a black hole has a fixed relationship with the speed of light? Are we saying that?
Bro, can you listen to me like 1 second?
Because if we're saying that, then no matter what the size, whatever the mass of all these black holes are, then why is it all the same?
What if, wait, listen to me. What if we can't measure it with acceleration at all? Because look, according to relativity, when you go in the speed of light, time goes slower. Acceleration definition is the rate of change of velocity with respect to time. And near black hole, time also goes slower. So like, it makes no sense comparing it with acceleration in the first place.
Look, acceleration is literally the only. What else are you gonna measure it with, man?
Yeah, we don't know yet. You gotta find something out.
You can just say we don't
And
know
even
yet.
if we do it, like, what do you expect us to do? Like, calculate the time?
Exactly. What else will you
Because
do? It's
time goes
acceleration
super
that you can
slow.
look at
Hence,
it.
acceleration is super
All
slow
right,
in
then,
black
man.
hole.
Tell me, what is the acceleration past the event
It is-
horizon? What you experience? Is it zero?
Then the only thing that can explain here is that acceleration is super slow because time goes really slow there.
Shubham,
And
listen.
Yeah.
If we're saying, which you guys were saying, you were saying that the surface gravity of a Schwarzschild black hole is it to be inversely proportional to the mass of the black hole, right? But if the event horizon represents the point of no return, even for light, then I would have the thought that surface gravity must have a fixed relationship to the speed of light, and hence should be the same for all black holes, regardless of mass. Right? Is that what you're saying? Well, then why is it so? It should that's
mass is important, very important.
exactly. But then, even if mass is important, every single time light will get sucked in.
If you see my screen over
I see
here,
No, not really. Look, it
listen,
depends on the
even
mass.
if
Okay.
arithmetics are correct,
over
Because look,
there might be a logical
more the
error.
mass, more the radius, it'll suck in light. Okay, look,
What does a radius have
a
to do
mass.
with it?
Okay, no, it has, because more the mass, the more the radius of the black hole.
Not
It sucks
necessarily.
in light. Okay, look, it has more area to cover. Okay, it makes sense.
No, mass
Yes.
doesn't. What? Bro,
Okay,
so
look.
you're gonna have like
Does
the
that
I will-
smallest.
Let's take a small black hole and let's take a huge black hole. Obviously, the huge one has a greater mass, and like, if a light passes through, suppose let's say the diameter of the smaller one is like some 5 something,
let's
some
take
trillion billion, we don't know,
black hole.
and the other one's like 10 billion something, and the light travels at 8. The smaller one won't affect it, but the larger one will. So mass does matter.
You do realize that you can have like the smallest black hole, but it'll probably have the same mass as a massive black hole.
no the mass and the
not
radius.
really.
Vamsi, the mass and the
What is
radius
this?
have a fixed proportion, right? They have a fixed ratio.
Yeah,
Yeah.
yeah.
So I don't think that's possible that like a small a black hole with a really small mass has like
Yeah.
a really huge radius.
Yeah, that's not possible.
Exactly.
bro,
So,
because
so listen, we're all using
Density is a constant.
stellar mass black holes is what we're using, right?
Sure.
Right?
Yes.
Yeah. So if we're using one of those, and we're using, let's say, on the other hand, a mini black hole, which is also a type of black hole, both of them would have the ability to do the same thing of negating all these objects passing the event horizon, which is only. It's not like it's a property. It's like they just have the ability to do so, no matter what the mass is. So mass shouldn't have to do anything with this, because if you want a black hole to exist, then it should have a specific boundary of mass that it passes, so that it even is counted as a black hole.
mass is super important for everything, especially a black hole.
Shubham. This
Yeah.
is the ratio between the final acceleration at the event horizon, and the mass, right?
Yeah.
Yeah, this is the ratio where h is the Planck's constant. And here's the proof.
But mass is super important though.
Mass is
Quantity,
important, Ray. That's why I found the
Yes.
ratio using mass. And then using mass, I used the previous equation and equated it to R, right? So I found a ratio between acceleration and the radius. Now the ratio also I can equate it to CT by 2. And I can find the ratio between acceleration and the amount of time it takes for a body to get sucked into a black hole.
Yeah, but then this time is like people who are outside the black hole, right?
Yes.
It's
Because
not for the
we did
people
not
going
consider,
inside a black hole
yes,
because time
we,
changes completely there.
we did not consider time dilation when we talked about
Yeah.
this. So this is for an observer outside observing this from an infinity point who has not been impacted by any kind of gravity or anything that could change the speed of time, if that makes sense.
We have discussed this topic thoroughly, and we have come to the conclusion that there is no conclusion. I feel like this is a great start for Think Tank Science Club. I'm eating an apple right now, so my mouth is kind of occupied. But I find this to be very fun of a topic to discuss. We didn't get to discuss space debris because Mr. Think Tank didn't let me do it. What a nerd. Anyway, I